So in last video, we introduced the gradient descent algorithm for searching the omegas for the decision boundary in the linear decision problem. But we know the computation for this algorithm is very slow due to the checking if every data point is correctly classified. So this gives us very slow algorithm. So a better way to do this is instead of checking this sign at every data point and calculate the gradient, we check only one misclassified point. So this idea is called the stochastic gradient descent algorithm. Gradient algorithm. Okay. So the idea is just at each step pick one. So we're only checking one data point misclassified. The data point xi. And at each step. Second is, and then check gradient descent. Loss function. L only at one data point xi. Inner product is omega and yi. Remember, this is just equals to the negative, because this is misclassified. So this loss is function is negative yi multiply xi. Inner product is omega. Okay, and then we can check the gradient. It's just calculate the gradient on one data point. Yeah, so that's the idea, and maybe you can little bit summarize a little bit. So this gradient, stochastic gradient algorithm is, well, there are some misclassified point. Misclassified. If there is a point misclassified, then we update omega by using the omega plus. Remember, the gradient is just the front part, and we take the opposite sign, so it's yi xi. So that's the stochastic gradient algorithm. So the computational cost is only each step only take d computational cost. Okay. Stochastic gradient descent algorithm is quite popular. You will see this algorithm be applied to many machine learning algorithms along the semester, especially for the neural networks. However, the stochastic gradient descent algorithm does not work well for every problem that gradient descent works for. For example, the precision risk function happens to have the special property that guarantees the it will always give a solution for this problem, but this does not guaranteed for all the other cases. Okay. So now we solved our problems, right? Do you remember the original idea? The question we have is, given the data point, we want to find the linear decision boundary, right? Linear decision boundary means we want to find this omega. Now we introduce the interpretations and then we introduce the algorithm to find this omega. But there is still a small problem there. That remember we restrict our decision boundary cross zero by restricting alpha equal to 0. Okay. So now in general, what if alpha is not equal to 0? How can we apply this algorithm? So I will talk a little bit here. So what if our decision boundary does not pass through origin? Actually, the trick is very simple. So in other words, if alpha does not equal to 0, we can still apply the algorithm we just introduced. Fx equals to omega times x plus alpha, right? This is our decision function, and this can be written as, for example, if we had two-dimensional case, omega 1, w2, and alpha, and then we have the point feature space is x1, x2 with a constant 1. Okay, so we can think this is our new omega matrix for this problem. So like omega star, and this is our x star. Okay, so we again write down this as omega star dot product with x star, and we can then apply the algorithm we developed before. Stochastic or not stochastic gradient descent algorithm. Okay, so yes, so that's the trick we use here. Actually, there are a little bit of story about this famous machine learning algorithm. This is a picture of the Frank Rosenblatt. And this is the perception algorithm he originally developed at the Cornell Aeronautical Laboratory in 1957. Okay. He said the electronic computer expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So we're still looking forward to this machine learning development. Okay, so far this algorithm and this is known as a perception algorithm. Okay, so we conclude this is called the perception algorithm. just by searching the weight using the stochastic gradient descent algorithms and find the linear classifier. And there is a why this is so important, because this has very nice property that it has a theorem, convergence theorem. So it's called a perceptron theorem. If data is linearly separable, perception algorithm will find a linear classifier. That classifies all data points correctly. At most, with maximum of the iteration number can be calculated. So R over gamma square. This is gamma square. So this R is just the maximum vector length. This gamma equals to the maximum margins. Okay. So not only we have a useful algorithm, but there is a theory behind. So if we have the like if you have two class generated separated from the Gaussian distribution, we can always find a solution, a linear classifier to separate them.